Okay, so I did notice a little mistake, so I stopped the recording and restarted it there. So I had actually imported the function improperly into GeoGebra, but if we have the correct function in GeoGebra and we do try to find this intersection, we notice it's going to happen around negative 5.4 and 10. Okay, so now that we've got that, we want to say that when t is about negative 5.4 or t is 10, then we have solved this equation. However, we now need to look back to what our variables mean, and we need to ask ourselves, do these values make sense in the context? So t happens to be the number of years after 2020, right? So we shouldn't necessarily be able to have a negative t value, right? Negative t would correspond to years before 2020, and that's not included in our projection. So we need to stay inside our model, right, and say that this t value of negative 5.4 is not going to make sense in our context. So that being said, we know that t equals 10 does make sense in our context. T equals 10 corresponds to 10 years after 2020, which would be the year 2030. And so applying this result into our context would say the model that we have predicts that the number of 5G subscribers worldwide would be 2.951 billion 10 years after 2020. Or in 2030, the number of 5G subscribers worldwide will be 2.951 billion. Okay, now if we've got this function here, we want to graph it and find the solution. So let me go back to my graph, right, and we can graph this function here. It was x squared plus 1. Right, so if that is the case, then let me zoom to fit now and scroll back out a little bit. Okay. Let me zoom to fit again, and let me hone right in on this vertex and then do it one last time. Okay, so now we can see this graph on our XY plane. Right, here it is. We can see that it doesn't cross the x-intercept. Well, if this function doesn't cross the x-intercept, what can we say about solutions to this function? What if we tried solving it algebraically? Right, so if I said x squared plus 1, I want to find the solutions of this equation, so let me set it equal to 0, and then try to solve. Right, so x squared plus 1 equals 0. I've got to move 1 to the other side, and that'll read x squared equals negative 1. Using my square root method, I find x equals plus or minus the square root of negative 1. There should be some cognitive dissonance now, because more often than not, up until this point, we've been told that we can't take the square root of negative numbers. It just isn't right. And so what it ultimately means, right, is that there's no solutions in the real number system here. And we can visually see that by verifying that this graph does not cross the x-axis. So there's no x value such that the y value is equal to 0. Okay, and that means there's no real solutions to this, right? The solutions may exist, but they're just not real numbers. Okay, so little sidebar here. If we want to help figure out how to solve these quadratic equations, we've got a couple different types of graphs that could happen. Right? We've got a graph where the graph crosses the x-axis twice. And in that case, we're going to say the equation has two real solutions, right? There's two values such that when we plug them into our function, we get an output of 0. Right? That's the graph crossing the x-axis twice. Okay, and if this is the case, we want to use factoring or graphing or the quadratic formula, whichever is going to be simplest for us to work with. Okay, well, the other situations, we've got one where the graph touches but does not cross the x-axis. And what this means is that the equation has only one real solution, right? There's only one value of x, then when you plug it into the function, you get y equals 0, right? And it happens at the vertex there. Okay, if we want to try to solve this kind of equation, we're going to want to factor or graph or use the square root method, right? Those are going to be our best case scenarios there. But we do have one more scenario. If the graph does not cross the x-axis at all, then the equation has no real solutions, and we want to use the quadratic formula to verify the solutions are not real, right? And if we do, we'll end up with some negative square root in our answer, which means that the solution is not real. In fact, it's complex. All right, now we're going to talk about that complex number system. So some functions have zeros or solutions that are not real numbers. The complex number system is used to find zeros of functions that are not real numbers, right? So this is kind of how we help fill in our holes, right? So when we look at the graph of a function, if the graph doesn't cross the x-axis, then it has no x-intercepts, and thus it has no real number solutions. Okay, so here's how we can view the complex plane. So we've got our real x-axis, and then we've got the real y-axis. Right, and then we're saying we've also got this third dimension that has to do with some people call it the imaginary part of x. I like to call it the complex part of x. Right, so if we have the real version or the real component of x, so anything that doesn't have a negative square root in it, and then we've also got the complex portion of x, that part that does have the negative square root in it. If we treat each of those parts like they're their own individual, then we can make a three-dimensional graph, right, where we treat the real component of x as our x, we treat the complex component of x as another direction, and then we have our third direction to be the output of our function, or the y value. Okay, so talking about these number systems, we've kind of worked our knowledge base up through some of these number systems. So like when we very first started thinking about numbers way back when we were knee-high, we could count with them, right? We could say, I've got 2 sticks and you've got 5 rocks. Like, there we go, right? So those were our counting numbers, 1, 2, 3. We can see that there is a way for us to map these numbers to the real world, and it helps us. Okay, well, then we said, well, we can't really do cool math with these sort of numbers, so we need to have more in them. And so then we move from the natural counting numbers to the integers. And we're going to have things like 0 and negative numbers now, so we can subtract. Right, now we can also add as well. And so then we can start applying this to the real world and saying, oh, well, you know, you have 1 stick, and I am going to take that 1 stick. Right, and now you have no sticks. So there's how we can add subtraction into our list of operations that we can use when we're in the integers. But we still said, hey, that's not quite enough. You know, we said we got to do something more. We got to be able to divide these numbers, right? So if I have 1 bucket of grains and I have 4 people around, I want to be able to equally split up my grain among these 4 people, right? And so then each person would have 1/4 of a bucket of grain. Well, we know that 1/4 is not an integer. Right, so then we now have to include these rational numbers or ratios or these fractions, right? And then now once we've got our fractions, we can do division. Okay, but again, we still said that's not enough, and the reason why is kind of a little bit above the scope of our course, college algebra, but we do then introduce these things called real numbers, right? And when we have the real numbers, then we've also got these numbers that weren't rational, right? Like pi or the square root of 2. So once we have real numbers, then we can do like square roots and other sort of operations there that include these irrational numbers. Okay, but again, still that wasn't enough, right? Because we wanted these numbers to help us to solve things, right? And once we've introduced equations, we just found out that there's some equations that we can make that don't have solutions that are in these real numbers, right? So we've got to extend it a little bit more and introduce this idea of complex numbers, right? And so the complex numbers are all going to have some multiple of this negative square root, which we call I. Okay, well, we say that the square root of -1 is equal to I. So this is what a lot of people call the imaginary part of a complex number. I like to call it the complex part. Okay, and with this, we know that when we square both sides of that equation, we get -1 equals I squared. Okay, so that's an important fact, right? The square root of -1 is I, and in turn, I squared is -1. Okay, so now we're going to want to try to work with this new complex idea. So if we have a negative square root, we should be able to express that in terms of I. So for example, if I've got this one A here, we've got the square root of -7. Well, from my square root rules, I know that the square root of -7 is the same thing as the square root of -1 times the square root of 7. Okay, but I know that the square root of -1 is I, so I now have 7 square roots times I. Okay, for part B, we've got square root of -16. Well, that's the same as square root of -1 times square root of 16. So I've got I times the square root of 16. Well, I know that 16 can be 16 is actually a perfect square root, right? And its square root value is 4. So rewriting the square root of -16, we can rewrite that as 4I. Okay, question C says the negative of the square root of -13. Okay, well, -13 is -1 times 13, so this becomes the negative square root of -1 times square root 13. And so then we'll have -I square roots of 13. Okay, negative square root -64 is the same thing as negative square root of -1 times square root 64. Well, that's going to be -I times the square root of 64. Well, the square root of 64 is just 8. So we'll have -8I. Okay, last one here, part E. The square root of -48 is going to be the square root of -1 times the square root of 48. 48 is 16 times 3. Yeah, 48 is 16 times 3. I just double checked it with myself. So that means the square root of -48 is going to change into the square root of -1 times the square root of 48, or I times the square root of 48. But we just said that the square root of 48 can also be represented as the square root of 16 times the square root of 3. So we'll have I times the square root of 16 times the square root of 3 but square root 16 is a perfect square root. So we'll have 4i times the square root of 3. Okay. Alright, now at this point I'm going to give y'all a minute to try these out on your own. Okay, so hopefully you guys got these answers. The negative square root of negative 8 is negative 2 times I times the square root of 2. The square root of negative 9 is just 3i. And then the square root of negative 108 is 6 times I times the square root of 3. Okay, so basically we're going to say that a complex number has this form here. Right, we've got some a and some b times I. Right, where a and b are real numbers. We say that a is the real part of the number, and then we say b is the imaginary part, or the complex part. Okay, so now we can use this idea of complex numbers along with our square root method to still solve these equations, right? But we're just going to recall that sometimes our answers may be complex numbers. Okay, so for example, if we've got x squared equals negative 9, then from my square root method I know that x is plus or minus the square root of negative 9. Well, the square root of negative 9 is 3i. So x has to be equal to plus or minus 3i. Okay, for part B, we've got 3x squared plus 24 equals 0. So to do my square root method, I've got to move this 24 to the other side and then divide everything by 3. If I do that, I'll get x squared equals negative 8. Okay, now I use my square root method that tells me x is plus or minus square root negative 8. Well, square root negative 8 is going to be I times the square root of 8. And the square root of 8 is 2 times the square root of 2. Alright, because 8 is 4 times 2. Break it up, simplify it, and we get square root of 8 is 2 square roots of 2. So, if x equals plus or minus square root of negative 8, then we're going to say x equals plus or minus 2i times the square root of 2. Okay, now we can also deal with this not just with our square root method, but in our quadratic formula. So if we want to solve something a little bit more complex, we can use our quadratic formula and point out our a, b, and c values, plug those into the formula, and then we'll find the solution of x. Okay, so if x squared minus 3x plus 5 equals 0, then a is 1, b is negative 3, and c is positive 5. So plugging this into my quadratic formula says negative b plus or minus the square root of b squared minus 4ac, all divided by 2a is going to be my solution. So let me plug my values in. I'll have negative 3 plus or minus the square root of negative 3 squared is 9, so the square root of 9 minus 4 times 1 times 5. Those are my a and c values there. And then all of this is divided by 2 times a, so 2. Okay, now we got to simplify it. Let's work on this root first. So under the root we've got 9 minus 4 times 5. So 9 minus 20. That's going to be a negative 11. Right, so under my root I've got negative 11, which means that x is negative 3 plus or minus the square root of negative 11, all divided by 2. Alright, and I need to take this square root of 11 square root of negative 11, pardon me, and I need to simplify it, right, using I. And so if I do that, then I'll have x is equal to 3 plus or minus I times the square root of 11, all divided by 2. And so if I break this up into its separate fractions, I'll have 3 over 2 plus or minus I times the square root of 11, all over 2. Right? I just put that 2 over both my pieces and separated it by the operation plus or minus. Okay, so when we see something like this, like 3 halves plus or minus square root of 11 over 2 times I, we have to remember that this notation means that there's actually 2 solutions in here. It's saying that x is 3 plus I square root of 11 over 2, and x is 3 minus I square root of 11 over 2. Okay, so there's 2 solutions in there. Okay, and if we work through b, we're going to again plug in all our values. Right, we'll have to add that 3 to the other side before we can start, though, because we know that to solve these using the quadratic formula, we have to have our standard quadratic form equal to 0. Okay, so plugging those values in, we'll have b is 4, so negative 4 plus or minus the square root of 4 squared is 16. And then we'll take 4 times 3 times 3, and we'll subtract that under our square root. So 16 minus 4 times 3 times 3. And so if I do that, 16 minus 4 times 3 times 3, that turns into a negative 20. Okay, and all of this is over 2 times a, so 2 times 3 is 6. And so now we've got negative 4 plus or minus the square root of negative 20 all over 6. Okay, but we've got to kind of break up that radical still, right? We know that we can reduce this and simplify it some more. So negative 20 under the square root can be broken up as the square root of -1 times 4 times 5. Right? And then using our product rule for these square roots, we'll have the square root of -1 times the square root of 4 times the square root of 5. Okay, simplifying that gives us 2i square root of 5. So the square root of -20 is 2i square root of 5. Okay, that means our solution x is -4 plus or minus 2i square root of 5 all over 6. Okay, I'm going to break this up into its pieces now. So x is equal to -4 over 6 plus or minus 2i square root of 5 over 6. And then I'm going to simplify these fractions, and I'll have x is equal to -2/3 plus or minus I square root of 3 over 3. Or excuse me, I square root of 5 over 3. Okay, and again, since that plus or minus is there in here, those are two solutions in one, right? We'll have -2/3 plus I square root of 5 over 3 and -2/3 minus I square root of 5 over 3. Okay, and with that example, I have finished the content for this section. So please go ahead and try to work on the homeworks associated with this section and the sections we've been working on. Try to stay up to date with that. And I hope you enjoy this winter weather. I will see you guys on Friday.